Curious? Look at this photograph of a crowd recording a concert. Every single glowing screen here is capturing millions of pixels of light in a fraction of a second. We pull phones out of our pockets and freeze reality without a second thought. Yet for most of human history, the basic mechanics of how we see those images remained a mystery. For centuries, the leading explanation was the Greek emission theory. Many thinkers of antiquity believed our eyes projected invisible beams outward, like flashlights, scanning the environment and striking objects so we could see them. Scholars spent hundreds of years building complex models around this idea, misinterpreting the very sense they were using to read and write. The person who finally demonstrated how vision actually works was an 11th century scholar named Ibn al-Haytham. Born in Basra, he was an ambitious mathematician who made a very dangerous promise. He told the ruling caliph of Cairo that he could build a massive dam to control the unpredictable flooding of the Nile River. The caliph agreed and brought him to Egypt, but when Ibn al-Haytham actually traveled upriver and saw the raw, violent power of the Nile firsthand, he realized the engineering task was impossible. And in 11th century Cairo, failing the caliph was a fast track to execution. To save his own life, Ibn al-Haytham made a desperate calculation. He feigned insanity. He acted the part so convincingly that the caliph spared him, opting instead to place him under indefinite house arrest. Stripped of his freedom and locked away from the outside world, he had nothing left but time and isolation. He didn't know it yet, but that empty room was exactly the laboratory he needed. This artist's rendering shows his confinement. Trapped in a darkened space, a tiny hole allowed a single beam of daylight to pierce the shadows. On the opposite wall, that breach was projecting a moving picture of the outside world directly into his room, completely upside down. Ibn al-Haytham proved a crucial law. Light travels in perfectly straight lines. Through a tiny aperture, straight rays from an object's top are forced downward, and bottom rays travel upward. They cross at the pinch point, naturally flipping the projection into a camera obscura. This projection dismantled the old Greek models. Humans clearly weren't shooting beams from their eyes. The tree was projecting its own light. To understand if this applied to vision, Ibn al-Haytham studied the anatomical descriptions of the eye recorded by the Greek physician Galen. By comparing the structure of the pupil and the retina to the pinhole and the back wall of his cell, he realized the human eye was actually a biological camera obscura, a receiver of light, not a projector of it. He didn't stop at theory. He gathered lenses, curved mirrors, and various physical tools to test light refraction and reflection. He isolated variables to observe exactly how light behaves when passing through different media. Over the next decade, he compiled hundreds of these rigorous, mathematically verified experiments into a massive 7-volume text known as the Book of Optics. His insistence on running physical trials over and over again established a new standard. He demanded that abstract theories be proven by observable, repeatable evidence, a practice we now recognize as the foundation of the scientific method. When the Book of Optics was translated into Latin, it became the definitive manual on light. Mathematicians and inventors, including Leonardo da Vinci and Johannes Kepler, built their own discoveries directly on top of Ibn al-Haytham's math. Look at this early photograph of an eclipse. Long before cameras, astronomers used the camera obscura to safely study these intense solar events. By projecting the sun's image onto a wall, they could safely chart eclipses and sunspots without ever blinding themselves. This diagram illustrates how 17th century artists shrank the dark room into a portable box. By adding internal lenses and an angled mirror, they bounced incoming light upwards onto a pane of glass. This allowed painters to trace landscapes with flawless perspective. An accidental discovery made by a man in a cell had evolved into a practical instrument for mastering both the stars and the canvas. By the 19th century, inventors replaced the artist's tracing paper with light-sensitive chemicals. Devices like this wooden daguerreotype allowed the projected light to burn its own image onto a plate, permanently freezing reality in place. Over the next century, chemical plates were swapped for film, and eventually for digital microsensors currently sitting in your pocket, from a stone room in Cairo to a 5mm lens on a smartphone. Every time you snap a photo, you're relying on the exact same geometry of light and the same demand for physical proof, first demonstrated by a scholar in a jail cell 1,000 years ago.